All right. For once, I have to turn on my webcam because today we are going to be we're going to be looking ridiculous. We're going to learn about magnetic fields, right-hand rules. We're at 4:30, so we'll go ahead and start. So, we are finally getting into magnetic fields, y'all. Whether that's good or bad, matter of perspective, but it will use some of the things we've talked about, mainly current. It will use our math skills from vectors, but these concepts, in my opinion, are going to be mathematically not bad, but they're going to be conceptually about even. I would say conceptually about even with the stuff we're doing in terms of difficulty, but they're going to require good spatial reasoning. These problems in particular are going to require good spatial reasoning, and we're going to be doing something called the right-hand rule. Actually, there's going to be technically 4 of the rules. And so we're going to be doing this whole thing, moving your hand in weird orientations. And the good news is, if your right hand's not great, you can technically use your left hand, but we'll talk about that. So there's some options. If not, we can discuss. Anyway, logistics. So I have received, our grader was awesome and extremely quicker than I expected, and he got all the free response graded. And so your final grade is now posted, and here's what I did. I took all the free response grades, and I basically looked at it and said, all right, I weighted it the way I told you all in the very beginning. 60% clicker questions, 40% free response. So I took those free response grades, I took the clicker grades, I calculated what that score would have been. If your score on the free response, on the multiple choice was better, I kept that. If your score on the multiple choice was better, I kept that. If your score with that original weighting was better, I switched to that one instead. That's how I ended up doing it. So it matched either what you expected, or if you devoted more of your time to the multiple choice, you benefited from that as well. I only did that for this one. Moving forward, my reminder to you all, my plan is 20 multiple choice and then 1 free response. I think that should be sufficient time-wise. As I design the test, I will try to be careful on my end, but I think that will be very doable given what I saw progress-wise as I was getting my steps in. I will tell you all, when I proctored that exam, I had more steps that day than like any other day as I was walking up and down and up and down. So one of the things I do when I'm doing that is I monitor kind of progress and see how far along people are to give me a sense of, unfortunately, I could tell quite quickly last time that there wasn't going to be enough time, but at that point there wasn't too much I could do about it. It was what it is. But that's why I'm walking around and looking a lot of times just to see the progress and reduce the barrier to asking me any questions. All right, so there you go. Test grades are posted. They're factored in. Great. As kind of the final of what it will be. Your discussion questions this week, I wanted to talk about normally I don't talk about the questions because you kind of go over them in the class, but this question in particular is the second discussion question I wanted to talk about really quickly because I did not teach you all how to solve these problems last week. So I wanted to just spend a few moments talking about it now, show you all how you will solve it, and then of course the TA should be solving it as well in front of you all. So let's get the picture. Let me grab that picture real quick. You all can see how organized I am. Let me grab the picture to go along with it. I should have had that. So discussion week 7, this is what I sent you all. So here's the picture. I talked about, these are called RC circuits. Why are they called RC circuits? Because there's a resistor, which is R, and there's a capacitor, which is C, RC. So here is how this problem says this capacitor is initially uncharged in position C. They flip it to position A, And that is going to charge the capacitor. It's connected to the battery, so the current will flow and charge the capacitor. It says it's connected like that for 10 milliseconds. After that 10 milliseconds, it is switched to B. We call this the discharging case. Why? It's no longer connected to the battery. So previously, it was getting charged by the battery. Now it's no longer connected, but there's nothing holding those charges on there anymore. So current will now flow. It'll discharge. I talked about it a little bit last time, but I didn't show you all the math. Here is the equations. These are uploaded online. These are the equations you're going to use. In the charging case, which is the first one, 10 milliseconds. I'll zoom in on this a bit just so it's easier to read. The voltage of the capacitor as a function of time, so just the voltage on this capacitor as it's charging, is the initial voltage, which or the max voltage, which I'll tell you is 12. So it's going to be 12 times 1 minus e to the negative t over RC. T is time, R is resistance, C is capacitance. So this is R, this is C, this is also R. If you want, I can call this one R1 and I can call this R2. In this problem, they are the same. They're literally both 150. So you will get the voltage that it's charged with. Then you will take that number and you will plug that in here. That will be your new V0. The V0 in the discharging case will be whatever you calculated from the charging. Plug it in. T is going to be the time it discharges for. R is going to be 150. C is going to be 40 microfarads. So that's how you're going to solve this problem. Reminder to you all, this is 10 milliseconds. So when you get time, it's going to be 10 e to the minus 3 seconds from the problem. Both of the times are the same. Okay? So it's just a math problem, but this is basically the idea. Get the charging voltage by using that equation. Get the charging, how much it gets charged to, then plug that into the discharging. I am not going to ask a question like this on a quiz or a test, okay? So I'm showing you all this now because, remember, I did not design the discussion section questions, but they are a part of this course, and I didn't want you all to see this problem and just be absolutely flabbergasted, okay? So that's the process. I will post these slides with this picture stuff as always afterwards, so you can look this over, but of course the TA will go over the answers as well. Speaking of discussion sections, the next week I sent you all an announcement, and I've heard some TAs have also notified you all. Next week is the March Physics Conference, which means all the physics grad students and professors will all be there. Not me, because I'm a high school teacher. The TAs won't, there will be some TAs that are out, and so because of that, attendance will be optional for your discussion section next week. We will still have class, we'll still be here doing things, but your discussion section, attendance is optional, but they still want you to submit, I still want you to submit the discussion, like solving the problems. If you try, it's based on completion, it's based on trying it. They're not looking if you have the exact right answer or not. Okay? Yes, sir. Don't believe so.
Because for me, it's due next week. I have two due on the same day.
Okay, let me check. I'm not gonna. I'll check that. I'll check that later. But each one should have its own week. Okay. Each one should have its own week. If that got changed, I'm not quite sure why that did.
I'll show you the last one.
Yeah, that'd be perfect. Thank you. All right. Yes.
Do you know if our labs will still be happening?
So labs are a completely separate thing from this course, and I have almost zero knowledge about what those are going on. So unfortunately, I have no idea. If they haven't sent you anything, assume it's still happening. Okay, so there you go, discussion question 2. Before we get into magnetic fields, I promised you all we would do a quick practice with combining resistors. So here's a quick clicker question where I found a circuit. I literally found this one alone. Making these things myself is a bit of a pain, so I'll tell you whenever I find these, someone else has made it, but that's fine, doesn't change anything. I have a circuit with a 5-volt battery that goes into resistor 1. It then splits into a path with resistor 4 and another path with resistor 2 and 3. After 4, it splits into 5 and RA. Those come back together, recombine with this, and go back to the battery. The question is, which should I combine first? Which resistors should I combine first? Should I combine R1 and R4, which are the ones up here? I'm going to zoom in because I know the font is a little small. Again, unfortunately, I didn't make this, so that's why the font's a little smaller. Hopefully that's easier to see. Should I combine R1 and R4? Should I combine R2 and R3? Should I combine R5 and RA? Or should I combine 1, 2, and 3? What should I combine first? Remember, whenever you see a problem like this, one of your first things should be, we got to get to a single resistor. We got to combine all those resistors to get to a single one. And so this question is just, what's the first step in that process? Which one should I combine first? I've already mentioned, I think I've mentioned this before, but it's very, very likely that one of the free response questions will be something involving combining resistors. Doing problems like this where you have to find the current in like R2, for example, or something. They're involved problems, but they test a bunch of different concepts together, which is why I think it would be a good free response. There's a bunch of steps involved. Again, this and this problem is just the first step. All right, I'm going to wait till 2 minutes. There's no math here. I didn't ask you to actually find what it was. 5, 4, 3, 2, 1. So remember the rule, and the answers here are looking great. The rule is you combine either if there's some purely in series or purely in parallel. That's what you're looking for. You're looking at the circuit and saying, is there any purely in series? And purely in series means no junction between them. Are there any resistors with no junction between them? Yes. These two. Now, don't get super disappointed right now, because there's more than one right answer to this problem. These are purely in series. There's no junction between them, so we can combine them. We can add those up. Then we also can check, is there any purely in parallel? Is there any that share the same wire kind of before and after them? And if we look at the ones up here, these ones right here share this blue end. Doesn't matter if the wire splits. All that matters is they share the same one. If that wire splits, that's fine. These ones share the red and blue on both sides. So these are purely in parallel. So what's the right answer? You could have picked that or that. You can combine either one first. Then do the other one second. It doesn't matter the order. So this one you have a choice of which you combine first. And then you would go from there, do the same process. Is there any purely in series, purely in parallel? So hopefully it lets me pick. Yeah, look at that. Great. First question I've had more than one right answer. But I like this problem because it lets you see that there's more than one path that gets there. You could do either one first. Purely in parallel, purely in series. After I combine R5 and RA, then I can combine R4 with that because those would be in series. Then that would be in parallel with this one, and then all that would be in series with that one. I'm not going to spend the time on it. I may have the time tomorrow. I can't promise this, but I may end up showing you all how to condense all of this. I'll let you know if I do that. So let's get into the stuff today. That was just a quick recap of that, a little bit more practice. Today, we are talking about magnetic forces, which are going to be due to magnetic fields. As I mentioned previously, there's some important concepts we need to remember. We need to remember what vectors are. We're going back to vectors again. Good news. None of the vectors in the problems we're doing, you're not going to have to do any trigonometry, okay? So electric fields and Coulomb's law, you end up having to do that. In this case, there's no trigonometry involved. I'm not going to give you a problem with that. They're too difficult to make because all our problems are going to be three-dimensional. So I say that as it ends up being a good thing. You'll see why. You need to remember that current is defined as positive charge moving, and what current is, which is that. And you need to remember centripetal force. Centripetal force, if you don't remember that, centripetal force was mv squared over r. If you had an object that was moving in a circle, so say I have something that's moving in a circle, just a ball or something, there is a force it is experiencing. Whatever, let's pick the easy, maybe it's gravity, maybe it's a planet orbiting the sun. In that case, the force due to gravity will equal mv squared over r. Centripetal force is not how to put this? It's not a fundamental force of reality. It's not gravity. It's not the electromagnetic force. The centripetal force is all the forces actually acting on it. If you add them all up, it'll equal mv squared over r. So if, for example, have a planet orbiting the sun, the force due to gravity will equal mv squared over r. We'll see that in some context today when it comes to forces, and we'll solve some problems. All right, so lots of things. Looks like a lot of things, but it's not going to be as bad as it looks. We're going to talk about which way magnetic field line, what magnetic field lines are, which are they point. We're going to use the right-hand rule to determine how a charge will move based on moving in a field. We're going to talk about why it's going to make a circle when it goes in a field based on that. We're going to talk about the direction, magnitude, of force a wire will experience due to a field. And long story short, we're going to find out that moving charges experience a force in a magnetic field. Moving charges will experience a force in a magnetic field. That's kind of the punchline of most of these all combined together. All right, why do we care about magnetic fields? These are extremely useful to you all. If you all have headphones on you, you are carrying a magnet. Every one of your headphones has a magnet in it. That's probably the most common thing. Your phone probably has a magnet in it. But most importantly, if you want to convert electricity to movement, you need magnets. So any motor of any sort, anytime you have electricity going in something and a movement happens, there's magnets involved. So magnetic fields are extremely important for today's society. I've talked about the importance of electricity. I didn't really have to sell that too much. I told you like electricity was like liquid energy and we convert it to various things. If we want to convert it to movement, we need this side of the coin as well. We need the magnetic side. So we've got the electric field side. Now we're going to introduce the magnetic field side and talk about, at some point we'll talk about how they come back together. All right, so before we begin, we have to introduce what a magnetic field is. What is this magnetic field? It's the field that's responsible for the force that moving charge experiences. I'll explain that in a second, but I'll read through the rest of this first. The unit is going to be the Tesla, named after Nikola Tesla. The company Tesla got their name from that guy. We get our unit from that guy. Very interesting guy, did all sorts of interesting things, a little eccentric, but definitely a genius. There is another unit called the Gauss, and it's literally just 10 to the minus 4 Tesla is 1 Gauss. We're going to be basically working in Tesla for this class. I'm not going to really give you any problems with Gauss. I'll double, triple check that after this class so that I'm not a liar. But Tesla is the main unit we're going to be using for pretty much every problem. The variable for magnetic field is going to be B. B is in boy. I honestly don't know off the top of my head why it is B. Obviously, the word magnet starts with an M. I don't know why they chose B. There's a history behind it. We can Google that at the end of class if you're curious. I don't know off the top of my head. But there's a reason. All you need to know is that, remember that variable is what's going to show up in an equation. So if you see an equation and you see the letter capital B in it, that's magnetic field. All right, directions. I told you all we're working in 3 dimensions, so we no longer have left and right, just left and right. We also have into the page and out of the page. Out of the page will be a dot, into the page will be an X. And to give you a sense of perspective, 5 times 10 to the minus 5 Tesla is the Earth's magnetic field. The Earth makes a magnetic field. Hopefully you knew that. That's how compasses work. 1 Tesla is a lot. A lot. To connect to your all's field, if you're in the medical field, an MRI machine, a magnetic resonance imaging machine, those things have about maybe 2 or 3 Tesla. Extremely powerful. If any of you have gotten an MRI, They hopefully told you to not have any metal. They checked if you had any metal in your body because it will literally rip it off of you. There's some good videos of like old MRIs, and they like put a chair, like a metal chair, and they hooked it up to a pulley to see how strong it was, and it looks ridiculous. Feel free to just Google that, like metal chair in your MRI, and it's they're very, very, very strong fields. And we're going to learn how they make those fields too. It's not by permanent magnets. So, lots of information on here, lots of information. I'm going to slowly kind of unpack this. Right off the bat, I introduced the field, and it's got a bunch of, the definition seems more complex than maybe you feel like it should. Maybe you just feel like the magnetic field is something that's outside of a magnet. Remember, fields are a made-up thing. Fields are made up. Does a gravitational field exist? You can't see it. A field is something we use to explain something we can see. We can see forces. For example, here's my water bottle. Look at that, a force acted on it. You can see that. You cannot maybe see the electric fields that interact here and see that. You can see that when I let go of this, it falls and it bounces. What is causing that? We said a gravitational field causes it. There's no string attached, so we say there's some field here that is pulling it down, and that's what causes it. The magnetic field is the same thing. We found someone at some point, I don't exactly know who, discovered that if you have a moving charge and you bring it near a permanent magnet, because that's what they had back in the day, it moved. If you brought a moving charge, shot some electrons right past it, those charges moved, they deflected, and they said, what's causing that? There's no string attached to these. Let's just make up something called the magnetic field and say that's what's causing it. So, the field is a made-up thing. How do we define it? We define it based on what it's doing. It's causing a force on a moving charge. Okay, great, then we got our units, talk about those, variable B. Let's talk about this direction situation. This is going to seem confusing at first, but the notation here is actually kind of nice. Out of the page means pointed at you all right now. So out of the page, out of the board, if you're sitting at home, it means it's pointed out of the screen at you. Think of it like an arrow. Like I have this written here, but I'll clarify. Think of it like an arrow that shoots out of a bow. That arrow, if it was pointed out of the screen at you, you would see the tip of it. You would see the tip of it, which is a dot. If it was pointed into the screen, you would see the feathers sticking out of the back of it. So that's how you can remember the notation. If you see the X, that's the arrow pointed into it. You're seeing the feathers at the back. If it's pointed out of it, you're seeing the tip of the arrow pointed towards you all. I still use that kind of way of thinking about it now, and we're going to see this a bunch. You're going to see why we need this. Unfortunately, with these problems, they're going to become three-dimensional almost instantly. You'll see why when we get to our first right-hand rule. So, magnetic field causes a force on a moving charge. Protons, electrons, those things. Okay, so this is just saying that again. A moving charge will experience a force to a magnetic field. Why? That's a great question. That's where theories come in. This is kind of a law. This is just what happens. If you have a moving charge and you bring it near a magnet, it bends. It will arc in some way. The force is perpendicular, meaning 90 degrees, to the direction it's moving and to the direction of the field. We're going to see how to get that. That may be a little tricky to kind of visualize. The force is going to be perpendicular to both the way it's moving and the way the field is going. We'll do some examples that'll help us see what that exactly means. It's hard to kind of understand that until we do some examples. No work is done on the charge because if you all remember the definition of work, work was force, distance, and the angle between them. So, in this problem, it says they're perpendicular. So if the charge is moving this way, the force may be this way. If the angle between those is 90 degrees, cosine of 90 is 0. So, a magnetic field does no work on a moving charge. What does this mean for us? And one easy thing to explain here, it will not make it faster, it will not make it slower, but it will change the direction the thing's moving. We're going to get to a circle eventually. It does make it go in a circle, but this will not make it move faster or slower. It will only deflect it. It will only change the direction it's going. And this down here is going to be very important. This is our equation. We see a cross product there, and a cross product, you don't need to know how to do cross products in here, but you do need to know that that cross product is equivalent to this. Just multiply times sine of theta, where theta is the angle between the way it's moving and the magnetic field. I'll draw a picture of that here. Say I have a negative, let's go with a positive charge. Let's go with a positive charge. We're going to see why we have to use a positive charge in a second. Say this charge is moving this way. Say the magnetic field is this way to the right. So the velocity is up to the right. The magnetic field is that way. There's your angle that you will be using. It's the angle between those two. It's going to be the angle between those two vectors. And we could do some, yeah.
The force is always perpendicular. Is it always sine of 90?
So in this case, this equation won't tell you the direction of force. We're going to have to do some weird hand things to find that. That's where we're going to use the right-hand rule, and we'll all look very silly during the test, and it'll be a great time. Yeah, that's one of the fun things during a physics test, during the second one, is looking around the room and seeing everyone doing this whole thing. It'll be great. If everyone's doing it, it's not weird, right? So this angle is just to calculate how strong the force is, but it does not tell you the direction of the force. That's a good question. I want you all to think real quick, and I'm going to move this over. Maybe I have a problem on this later on. I'm pretty sure I do. But let's think ahead. So that I gave you all that example. If I have a charge that's moving this way to the right, and it's in a field that's also to the right, I want you to think, what is the angle between those? And then what would be sine of that angle? If the velocity and the magnetic field are pointed in the same direction, we say they're parallel. What is the angle between them? And what would be sine of that angle? Try that in your heads. See how good you are with your unit circle? So first question, what's the angle between them? It is 0. Theta is 0 here. What is sine of 0? It is 0. So this is an interesting result. When they're lined up, when they're parallel, the force will be 0. When they're parallel, if a charge is moving the same direction a magnetic field is, the force will be 0. If they're perpendicular, the force will be maximum. We're going to see that in plenty more slides, but I wanted to show you all that now just because it lets you see how the equation works. When they are lined up, the angle is 0, and therefore the force is 0. Therefore, F equals 0. I'll write that down. Therefore, F equals 0 on this charge. The magnetic field will do absolutely nothing to it. Okay? All right, so let's start, let's learn about the fib. Right-hand rule number 1. This is why I turned on my webcam for you online folks. We'll see how this goes. I will warn you all, this part's going to be, again, I normally don't like to put the webcam on there because clearly it covers part of my slides. But if you're online, you're going to have to see my hand because there's no way I'm drawing a hand well on these slides. Right-hand rule number 1. How do we find the direction of the force? We are going to use, I'm going to show you 2 different ways to do this. 2 different ways to do this. Right-hand rule number 1. First, you kind of you have to use your right hand. It's called the right hand rule for a reason, and we will explore why. So, get a nice flat hand, and let's make a problem for this. Let's say I have a positive charge moving this way to the right, and let's say it's in a magnetic field that's pointed up. Let's give an example so I can actually do this. So, velocity is pointed to the right, magnetic field is pointed up. You get your hand. You point your fingers in the direction of V. So whichever way V is going, your fingers go that way. So, To the right. Now the question is, do I do it this way? Do I do it this way? We're going to find out in just a second. Should I do my hand upside down? Should I do my hand right side up? Here's the trick to this. So you're going to line up your fingers with V, and you need to twist your hand so that I can actually rotate my V towards B. Put your hands such that without moving your wrist, well, so that I can turn my hands from V to B. So this is one way of doing it. So V is to the right. How do I make it so my fingers can actually point up? I do palm up, and look, my fingers can now point up. What a good. We are curling our fingers from V to B. We're curling our fingers from V to B. That's one way to do it. Which way does your thumb point? What would you all call this? And sorry, I don't know people, this is going to be hard. I actually going to do it for. So it's to the right. I curl it up. How would you describe my thumb? Out of the page. Now you can see why we're having to do 3 dimensions. Out of the page, which we, remember it's like that arrow shooting? Out of the page. That is one way of doing it. Fingers in the direction, rotate your arm around. There is no way I can bend my fingers upwards. So that's how I know I have it backwards. If my hand's like this, I can't bend my fingers upwards. So this is the only way where I can curl my fingers. We often call it cross product to curl. So that's one way. Those online there, bam. You can see it's out of the page. Try for yourself. Here's the other way. I call it the fib. F-I-B. Force is your thumb, and I say I call it the fib. This is what a student in my high school, when I took physics in high school, AP physics in high school, a student came up with this, and I've kept it ever since, and it's been a nice little way. Fib. Force is your thumb. Current is your pointer finger, and your other 3 fingers are the magnetic field. B. Fib. F-I-B. Remember, current is positive charge moving. Current is positive charge moving. So we can do the same thing. F-I-B. So I is the direction my charge is moving, so I point my pointer finger in the way it's moving. I point B, my other 3 fingers, in the direction the magnetic field's going, and to that you get the same answer. Which makes sense, hopefully. We are going to do practice with this, y'all. This is the only way you can get good at using this right-hand rule, is practice. It's, if you have to contort your arm, you're probably doing it wrong. Really important. There's 2 things I need to make certain you will understand, and I'm going to add them here. First thing that's very, maybe it's just one thing. I've already said, I guess one of them, you have to use your right hand. You have to use your right hand. The second thing that's very important, right hand gives force on positive charge. The right hand, when you're using this rule, gives you the force on a positive charge. It has been very important that every example problem I've given you, it's been a positive charge. If this was a negative charge, just take a guess. What do you think would change? If my force was out of the board for a positive charge, which way do you think it's going to be for a negative charge? Into the board. Remember, positive and negative is basically the opposite happens with them. We will do some examples with this. Let's explore what happens if you accidentally think this is the left-hand rule, and do the same thing. I'm going to do the swinging door one. I like to think of it as swing, where I take the velocity and I kind of swing it in the direction of B. That's the curl one. If I use my left hand, my fingers in the direction of velocity, I swing it towards B, I'm going to get a force in the opposite direction. If you use the wrong hand, my thumbs point in opposite directions. So, make certain you're using the right hand for positive charges. If the problem is a positive charge, use the right hand. If it's a negative charge, either just say my answer is backwards, or if you really want, you can use the left hand. I would just use the right hand for everything, and your answer will be opposite for positive. Let's practice. We're going to do each of these situations so that we can get really good at this, because this is going to be, I don't even know what you call this. Is this concept knowledge? I don't know. Kinesthetics? I don't know. But this is important. maybe you could visualize in your head which way F is, but I've always used the right-hand rule, and that's what every physicist I know does. All right, first one. A. The velocity is out, so it's like kind of pointed towards you all. We'll imagine that that X is pointed towards you all, and the B is up. So, right-hand rule. Take your hand, point your fingers in the direction of velocity. I'm going to use the swinging door one because I like it better, the curl one. So my fingers should be pointed out towards you all. Yes, you may need to contort your body and point it back the other way. So it's pointed towards you all. Or again, if you're online, it's pointed on the screen. You can see how this gets a little tricky because my screen's pointed a different way than what I. So it's pointed out. Velocity is pointed out. And remember, I need to rotate my hands so that I can take my fingers and swing them towards B. B is pointed up, so I need to be able to swing my fingers so they point up. See if you can figure it out. You're going to look ridiculous. Don't worry, everyone does. I'm going to be up here doing the whole thing. It's like how my baby waves currently. So there you go. If it's cool for her, it's cool for you all. V points out which way do I need to rotate my hands so I can swing my thumb up. Or not swing my thumb up, swing my fingers up. So V points out. My swing, yep, palm up. Which way is my force? That way, to the left. I have to twist myself around because I'm backwards. So, for those online, finger out, swing it up. The force will be to the right. Notice, every single one of these is a positive charge. So we're going to keep using the right hand. All right, next one. Same thing. Take your fingers, point them in the direction of V. Turn your hand so that you can swing that V towards the B. What a saying. Swing that V towards... Gosh, it sounds wrong, but I don't know what it could possibly mean that would be bad. So I'm just going to trust it doesn't. So point it that way, and then which way do you need to rotate your hand so that it swings towards the B, which is pointed up. So it points that way. I need my fingers to swing upwards. So they do when I do it this way. And my thumb points into the board. Again, if you're online, bam, bam, into the board. So my force is going to be this way. Into the board. I've got a nice three-dimensional axis here, so I can do this. Generally, we'll use those X's and dots for into the board and out of the board. Ooh, the next one's nice. Point my hand in the direction of V. I can't swing it towards B. They're pointed the same way. We already answered this question. It's zero. They're parallel to each other. This is where the math supersedes the hand. Why is this one 0? Remember, F equals Q, V, B, sine of theta. Here, the angle is 0. We already talked about that. If V and B are parallel to each other, there is no F. There is no force. So in this one, the force will be 0. You can't do the right-hand rule because there's no force to begin with. There isn't one. It'll just keep going straight up and up and up and up and up forever and ever and ever. All right, D. Try it. I don't want to spoil it. Take your fingers, point in the direction of it. This is just something you have to do. You have to try it for yourself. Again, if you have some other magic way of figuring this out in your head, if you are able to determine which way B will be based on this, awesome. That's some really good visual spatial reasoning. I am not able to do that super well, at least not with confidence, so I use the right-hand rule. When I'm solving these problems, I sit there at my desk and do this, and you will end up doing the same. It's okay, it's fine. All right, so V points, what do you call that, towards you all and to the left. So bam, my fingers should point that way towards you all and to the left. I need to swing my fingers towards B, so I need to rotate my arms so that I can actually swing my fingers upwards. I do that, and my thumb points that way. Into the board, also to the left. Into the board, also to the left. When I get to my computer screen, I have to redo it, so it is pointed that way. Into the board, kind of pointed to the left. All right, don't worry. Most of the problems in the problem set are going to be doing this nonsense. Yay. Yeah.
Does the orientation of like the XY thing matter?
No.
It's going like up.
No, it doesn't really matter. Like, just whatever, if I give you something like this, for example, let's look at part B. That force would be in the negative x direction because of how the x is defined. That's you would, if I gave you a problem and I did specifically say which way is it pointed, generally it'll just up, down, left, right, into the page, out of the page is good by me. When it comes to these problems, I'm really just looking for, do you know which way it's pointed? So often the answers will be left, right, up, down, into the page, out of the page. You won't need to worry which way is x, which way is y, which way is z. All right. Let's see how we do, y'all. I do, we do, you do. Classic teaching strategy. All right. I've got a particle, a positive one. Very important. Very important that we keep recognizing that these are positive charges. A positive charge that is moving out of the board, or for you online, out of the screen. The magnetic field is pointed to the left. Which way is the force? And you can see here, yeah, up, down, left, right, into the page, out of the page. You are going to have to do the right-hand rule. Point your fingers in the direction of velocity. Rotate your arms so that you can swing those fingers so that they point towards B. At no point should your wrist be bending. Do not bend your wrist. You can twist your wrist to get it pointed the right way, but do not bend your wrist to make things happen. That's how you'll end up making a mistake. The direction of your thumb will give you the direction of the force. This is challenging stuff, and I'm seeing it in the responses. Again, it's one of those things you wouldn't think is challenging. Once you get it, you got it. If this was a high school group, if I had way less of you all, I'd go around individually and kind of help you with your hands, but sadly I can't. There's too many. All right, we will go to 2 minutes again, because it looked like. And 5, 4, 3, 2, 1. All right, y'all, let's do it. Flat hand, my B is pointed out, so I point it towards you all. I don't lift my hand too high so that I don't look really awful. Hand is pointed out. I can twist my arm around. I need my fingers to be swinging to the right, so that's I can only do it this way. Behold, my fingers swing to the right, and my thumb is therefore down when I do so. Put your arm in a way that your fingers can swing so that instead of pointing at B, they're now pointing at B. The good thing is your fingers can only swing so much, so, I mean, again, if you accidentally have your hand this way, you can't swing your fingers to the right. It's not happening. I can't curl my fingers to point to the right. Here, I can't curl my fingers to point to the right. Here, I can't curl them to point to the I can only do it back. Here, I can only swing to the left. That's the wrong way. I like to think of this B as like a door, kind of swinging in the direction of B. So I swing it. That worked. My thumb is pointed down. Once you have the right direction, your thumb tells you B is, or the force on this charge is going to be down. Good news, y'all, and for those online, so I have my hand, I need to rotate it so I can swing it towards, V is out, sorry, that way, and then swing it, and my thumb is pointed down. I have no idea if this is lined up with the webcam. I will just warn you all, for the next 3 weeks, being online is going to be a hard experience, because this is only the first rule of 3, 4, 3.5. We have a lot of right-hand rules, and if you're online, I'm going to try with this webcam, but it's not easy to kind of show this. There's plenty of videos online about this, y'all. If at any point you're stumped, just look up right-hand rule number 1, and you'll see a million videos. If I'm not doing a great job up here, as you're solving problems, you're having troubles. So, boom. All right. Same problem. But it says, what's the direction of the force experienced by a negative charge? I have the velocity pointed out. It's the same setup. The only thing that's different is instead of being a positive charge, it's a negative charge. So, see if you can figure this out. Let me start the clicker. V is pointed out, B is still to the left. Which way will a negative charge experience a force? Yes, sir.
Is there no formula for this?
No. It's the same formula. So it is F equals QV B sine theta. That will give you the strength of the force. It will not tell you the direction. Which, every time we've talked about forces, the equation never gave us the direction. When we had two positive charges, we just had to know they repelled. When we had a positive and negative, we knew they attracted. When it comes to vectors, the equations don't generally tell you the direction. You kind of have to understand the underlying concept, and then the equation will just tell you how strong that force is. That's a good question, though. Technically, the cross product is where this is coming from. The cross product gives us a vector that's perpendicular to both, which is what you're doing with your hand. There's no. This is the easy way. There's no other real way to do this, y'all. The easy way is using our hand instead of having to use it all in our head. Okay, so we'll go to 135. Give you all 10 more seconds. 3, 2, 1. All right. You're going to see me do the exact same thing here. I'm still going to use my right hand. My right hand is going to point, my fingers are going to point out. I'm going to turn my hand so that they can swing towards me. My thumb is pointed down, which is the answer we got last time. But remember, negative charges do the opposite. Negative charges do the opposite. So if a positive charge experiences a force that's down, a negative charge will experience a force that's up. You didn't actually even have to do, if you knew the answer to the last one, this one is the opposite. A negative charge experiences opposite force. Opposite force of positive charge. Of a positive charge. I'll put that in writing so it's explicit. A negative charge. Look, if you want to use your left hand for negative charges, that will also get you this answer. Or you can use the right hand and just say it's going to be the opposite. Let me prove that to you all. Velocity points out, finger goes, great. Same thing I just showed you all, it's the opposite, so if my thumb points down, I just point up. I'm using my right hand right now. If I use my left hand, velocity points out, my fingers curl, I need to orient them so that they can curl towards me, and my thumb points up. So if you really want, you can say my left hand is for negatives, my right hand is for positives, or you can just use the right hand for everything and say negative charges would be the opposite. Pick your poison. They both get you to the same location. Okay. So, if we look at, I just want to show you all the problem set in case you haven't looked at this section. Most of this section is doing this. Most of this section is not math. A lot of it. Number 2 is literally just 6 different examples of practicing this. Yes, number 3 is math, and we're going to do some of these. Number 5, concepts. Number 6, concepts. And then there is some more math. Concept. This one's not going to be as bad as it looks. So a lot of these, there's actually like half the problems are math, half the problems are just finding the direction. Because that's how important this is. All right, so it's just math. An electron moving at 4 times 10 to the 3 meters per second in a 1.25 Tesla magnetic field experiences a magnetic force of 1.4 times 10 to the minus 16 newtons. What angle does the velocity of the electron make with the magnetic field? I could technically I can't even draw a picture here because it doesn't tell you which way things are pointed. So in this case, I'm going to skip the picture drawing. If you want, here's a negative charge and it's moving. Like, that's about as much of a picture I'm going to draw here. Anything extra will probably just make things more confusing. Step 1, what is given? When it comes to these problems, one of the best steps, if you're looking at this, you're like, I have no idea where to begin. Just match the units to the variables. Just match units to variables. That's always a great place to start if you're stumped. It's moving at 4.03 times 10 to the 3 meters per second. So I just put that number, 4 times 10 to the 3 meters per second. There is only one variable that goes with meters per second. It's velocity. It's how fast it's moving. Meters per second is always velocity. So without even knowing how to do this problem at all, I can do that. I can do that for my next variable too. 1.25 Tesla. That's the new unit we've seen today. What does that one go with? Magnetic field. The variable for magnetic field, I'll remind you all, is B. So B is the magnetic field. I'll specifically clarify that in case, because it's weird. Why is it B? We'll Google it at the end of class and explore that. And it's got experiences a force of 1.4 times 10 to the minus 16 newtons. Newtons goes with force. If you're ever stumped in a problem, you can always just match the units to the variables, and that at least gets you going. That at least gets you started. Just playing the matching game is what I call it with my kids. Newtons goes with force, Tesla goes with magnetic field, meters per second goes with velocity. We got a starting place. This is the power of the 4-step problem-solving process. Without understanding how to do this problem at all, we can just go through these steps and we'll start to reveal maybe how to solve this. What angle does the velocity of the electron make with the magnetic field? We're solving for angle. Step 3, do we have an equation that has these variables in it? It's always nice during a lesson when there's only one equation that I've given you all. Hopefully it'll be very simple to think what that is. When it comes to the test, yes, you will have a lot more equations, and that's when, yes, it gets a bit tricky, and that's why we have to practice and get used to them. Hopefully, you probably have it written down. See if you can guess what that equation will be. It's the only one I've given you today. The only equation we've talked about today is F equals Q, V, B, sine theta. And we may look at this equation and be like, great, that's awesome, Dr. James, but sure I have F, sure I have V, sure I have B, sure I'm missing the angle, but what about Q? What's Q? And this is the beautiful thing. We can figure out what Q is. Yeah, it's a charge, well, in this case an electron, but they're the same number. Yes. In this case, we have an electron, so it's just a charge of that. And that's the beauty of this problem-solving process. When I did step 1, I was literally just going through these steps without really thinking too much. And just by going through these steps, I realized, oh, I need to put Q down. And I just look in the problem really quickly and say, it's an electron. I know the charge of that. We've done a million problems on that. So, now we've got Q as well. Woo-hoo. Step 4, plug and chug. I'm going to go ahead and solve for theta first before I plug everything in. So F equals QVB sine theta. Let me get that sine of theta by itself. I'm going to divide all the other crap to the side. QVB are all being multiplied, so I'm going to divide all of that over. So sine of theta is going to equal F over QVB. What's the opposite of sine? Sine inverse. So theta will be sine inverse of F over QVB. I am going to make a new slide to give myself enough room so that I am not having to be crammed. Copy all that over. This problem does not ask for the direction, and it wouldn't be possible because I didn't give you enough information. Okay, I see what's right. It does ask for the angle between, but it doesn't ask what the direction of force is, so we're not using right-hand rule or anything. This one's just saying, hey, what's the angle between the two vectors? What's the angle between Q and B? Now that I've kind of gotten to this point, we can start to draw a little bit more of the picture. So theta is going to be sine inverse of F, which is 1.4 e to the minus 16 over 1.6 e to the minus 19 times 4 e to the 3 times 1.25. And that will definitely equal a number. Be careful, if your calculator is in radians mode, it will give you it in radians. If it's in degrees mode, it will give you it in degrees. Pretty much, I tend to keep things all in degrees in this class. All our answers are in degrees, so that's a good safe bet to leave your calculator in degrees mode. But if you plug this into your calculator and you get a different answer than me, if you get something that's really small, that could be why. That could be a reason why. And we get 10.08 degrees. That is the angle between B and D. Okay. So incidentally, for good or for bad, the math problems in this would maybe end up being simpler for us than the whole hand situation. But you'll get the hand thing down, the right hand rule down if you just practice it enough. It's just going to take some practice. Some of you it's probably already clicked. Some of you are going to need to spend more time on it. I cannot predict who it will click with and who it won't, but it's one of those things you got to keep trying till you understand it. It's either you get it or you don't. There's not really an in-between when it comes to the right hand rule. If you are confused about it, please, 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 go to my office hours, go to the help room, go to someone individually. Yeah. No, so I left my answer as a positive 1.6. You got a negative angle. Those answers will basically be the same. A negative angle and a positive angle basically mean the same thing in these contexts. That's a great point. If you put the negative in here, that's fine. I will pretty much always define angles as positive. If I want this to be a negative angle, I could just like turn my head upside down, and that would kind of be the same thing. A negative angle and a positive angle are the same amount. It's just a matter of perspective. So that's a great point. If you want it, I'm going to leave it as positive because all my angles will be positive when I plug things in. But case in point, sine of negative 10.08 is the exact same as sine of negative 10.8. So if we wanted to draw this picture maybe a bit more accurate, well, both are correct. Both are correct. I could have this, or I could have the B kind of pointed down and the velocity here. There was no frame of reference in this problem, so what's up, what's down is arbitrary. But that's a great point. I'm not going to try to trick you all with that on a test or anything. You don't expect a problem to have like a positive 10.8 and a negative 10.8. Yeah. Yeah.
Can we assume that Q is always going to be positive 1.6 to negative 19?
If it's an electron or a proton, yes. The problem may tell you I have a charge of this amount, in which case you would need to use that number. Yep. Same question, yeah. If you have a proton or an electron, it's a charge of a proton or electron. If it's a different charge, let's see if the next, let's just look at the problem set real quick. See if there's a problem like that. For example, right here, suppose a supersonic jet has a 0.05 microcoulomb charge. That's what you would use for charge in that problem. All right. Magnetic fields, this is just a kind of a quick important thing to know. Magnetic fields point away from north sides of magnets. So if you have a permanent magnet, the magnetic field lines point away from the north and towards the south. That's just a very simple, easy rule, but we need to know that. And you can see here a bunch of different situations of what it would look like if you have a bar magnet. one bar magnet, they go all from the north and then curl back into the south. If you have a north and a south, they go away from the north into the south. If you have two north, they kind of repel each other just like the magnets would. Magnets do the same thing that charges do. Opposites attract, like sides repel. If you've played with magnets, you'll have experienced that. North and south will attract towards each other, which is why the lines go towards each other. The north and north will repel each other. So this is just a quick intro to how, there's not really much to say here. How do permanent magnets make magnetic fields? Before I even begin to explain any of that, you don't need to know it. So that's good. What I'm going to teach you all right now is my limit to my knowledge on permanent magnets. There is going to be almost no problems involving permanent magnets. Why? Because they're complicated to solve. In fact, I have never in any of my physics classes ever seen an equation for the magnetic field due to a permanent magnet. As weird as that sounds, because it may seem like the most obvious thing to start with. The very quick and simple answer is how do you make a permanent magnet? Individual electrons are individual magnets. It's a very simplified explanation. They have something called spin. In chemistry, you all have heard of spin. Spin makes a magnetic field, electrons make a magnetic field. If you line them all up, you got a permanent magnet. I may explore that more later on, but I don't want to spend too much time on that because I don't want to go down a rabbit trail here. But for now, they point away from the north and towards the south. The Earth, this is kind of a fun little question. This is to test your knowledge of what I just mentioned. The Earth's magnetic field looks like this. It comes out of the bottom of the Earth and goes into the top of the Earth. Where is the north magnetic end of the Earth located? If I drew a magnet on top of my Earth, where would the north end of that magnet be? Would it be at the top of the Earth, or would it be at the bottom of the Earth? If I drew a magnet on top of that Earth with a north and a south end, where would the north be? Would it be at the top of it or the bottom of it, based on that idea I just talked about in the last slide? And this is literally the last slide on permanent magnets. That's how much we're going to talk about permanent magnets. 2 slides worth, and then we move on. All right, let's go till 125. No math here, no right-hand rule. 5, 4, 3, 2, 1. All right, let's look at our picture here. Magnetic field lines point out of the north into the south. They point out of the north. These ones are pointing out. These ones are pointed in. So if I want to put a magnet over this picture, north is actually on the bottom, south is on there. It's really weird. Just kind of a fun fact, the Earth's magnetic field, if we put a magnet over this Earth, if I drew a magnet right here, the north would be down here and the south would be down here. And your question is, then why do we call north north? Why do we call the top of the Earth north then if it seems to be backwards? Here's why. How do we measure north? What do we use? A compass. And let's imagine a compass is literally a magnet. A compass is literally a magnet. So here's my magnet. Opposites attract. So if this is the north down here, what end is going to be attracted to that? I heard some people say it very subtly. The south end. Opposites attract. And the south top of the Earth is going to attract the north end. So a compass points north, aka the compass itself is up and down, because the Earth's magnet is the other way. So, just kind of a fun fact for you all. Why is the top of the Earth called north? Because that's where your compass would point, and the north end of your compass points that way. But it's pointing towards the south magnetic pole. The opposite. Also, fun fact, the Earth's magnetic field flips every now and then. So at some point, the Earth's magnetic field will flip, and every compass in the world will point the opposite direction. When will that happen? I don't know. Maybe sometime in the next few hundred years or something. Why does it happen? I don't know. They don't really understand. How does this thing make a magnetic field? We got to learn a bit more before I can give you that answer. All right. Let's do some more right-hand practice, and this is going to ease us into the next thing we're going to talk about. I won't spoil what that is because it's going to give the answer here. Imagine I had a magnetic field that filled this entire paper, all pointed into the page. All pointed into the page. So X is everywhere. These are the magnetic fields. They're pointed into the page, and I have a positive, let's make this a positive charge so you can actually predict the direction. Great, magnetic field everywhere. Everywhere on this page. This charge, I'm going to tell you it's going to experience a force, and that's going to cause it to move, but then which way will it move after that? Which way will it move after that? Which way will it move after that? What will the path of this charge look like? What will the path of this charge look like? Will it just go straight up? Will it go at an arc? Will it go down? Will it go into the page, out of the page? There's a reason for this. The punchline will bring it all together. But first step, just find which way is this thing going to move right now? Which way is it going to move right now? Get out your trusty right hand. Again, if your right hand isn't, if you don't like your right hand, you're welcome to use your left hand, but the answer will be opposite. So, velocity is to the right. So my fingers go to the right. My magnetic field is into the page, so I need my fingers to curl into the page. I need to be able to turn them so they go into the page. And your thumb points up. Your thumb points up. So, at this time, it's going to experience a force up. What's that going to cause the particle to do if it's experiencing a force up? The particle will start to go this way. I mean, think of anything in the world that you nudge with a force. It will start moving in that direction. So its new velocity, after some time, let's draw it maybe like over here. Well, so it's going to experience a force up. So it's going to get nudged upwards, and it's going to keep getting nudged upwards. So here's my new velocity. My velocity got nudged. Think of a car that someone like pushed. It's going to start moving in the direction that you pushed it in. Do it again. Which way is the force now? You can get lots of right-hand practice with this. So after a little bit, it got nudged up, and it moved maybe a little bit up like that. The velocity got nudged as well, just like a car that you kind of pushed a bit. Fingers now are going slightly up. They're going into it. My thumb no longer points straight up. My thumb now points a little bit up and to the left. Same thing. What's that going to cause it to do? Now it's here. And let's just, it keeps doing this. It keeps nudging it to the left so that eventually the velocity is this way. It keeps nudging that velocity, keeps pushing it upwards. Now which way is it going to experience a force? Right hand rule, right hand rule, right hand rule, right hand rule. Fingers go up. They got to turn into the page. Your thumb should be pointed to the left, which is going to nudge it this way. All right, do it again. Some of you are starting to see the final picture here. Yeah.
Does this describe like the motion of like an electron around an atom?
This would describe a proton in a magnetic field. Unfortunately, it wouldn't describe it in an atom. In that case, that's just like orbit. It's a simpler, just electric fields are predominantly the force responsible for that. The electron's attracted to the positive, and just like a planet orbits around the sun, the electron orbits around that. So if you all answered this way, good job. Now my charge is up here. It's now moving this way. Do it again. Velocity is to the left. If you're online, I'll do this one for you. Velocity is to the left. My fingers need to curl into it. The force would be down. And hopefully at this point, you get the idea. I'll fill in the rest of it. Velocity, velocity, force, force. How would you all describe this? It's a circle. Remember I told you all at the beginning of class, we're going to do stuff with circles? This is why. A charge that moves in a magnetic field. Let's draw a better picture. Let's copy this and get rid of all the ink because it's a hot mess right now. A charge that is moving in a magnetic field that's uniform will make a circle. And it'll spin forever and ever and ever, never getting faster, never getting slower, assuming no air resistance or other forces. It will just spin in a circle. And this, one, physics-wise is interesting, but there is some tools that we're going to see some problems. Mass spectrometers use this. All right. So, see if you all remember the equation I gave you at the beginning of the slides. What is the equation for the force experienced by an object with mass m moving at velocity v and a circle with radius r? What was that equation that tells you the force of an object moving in a circle? And this is, we're going to get to a nice kind of point, a nice good point here. This stuff we're learning now has lots of medical applications. I'm going to talk about a couple of them with you all. And then I'll kind of be more to close out the class after this and after I introduce the equations. This has all sorts of very, very useful applications, especially in the medical field. All right, I'll give you all till 120. This is one of those. Either you know it, or you remember from the beginning of my slides, or you don't know it at all. And that's okay, because I'll give it to you now. In 5, 4, 3, 2, 1. Most of us did remember it very nicely. This is one of those that just is what it is. There's not really much to say about if you did not have it. This is called the centripetal force. Centripetal force, if you have an object that is moving in a circle, you can calculate its force using this equation. It does not matter what's actually causing it to cause. If you know its mass and you know its velocity, you know the radius of its orbit, you can calculate the force it is experiencing, even if you don't know what's causing it. Even if you don't know exactly what's causing it, you can use this equation. But in the last problem, we do know what's causing it. And we're going to go ahead and slap those two equations together. We do know what's causing it. So the centripetal force is the sum of all the forces acting on it that are causing it to go in a circle. And so we just said that the force, in this case, I'll straight up tell you the angle is always, the force due to magnetic field we said was QVB sine theta. In every one of these problems, angle is going to be 90 degrees. In every one of these problems, the angle is going to be 90 degrees. Sine of 90 is going to be 1. So that force equals QVB. So that's what's actually causing the force. That's going to equal the centripetal force. QVB equals mv squared over r. And let's go ahead and pull. We'll put it right here. There's all sorts of things you can calculate for this. You can calculate, if you know the velocity of the magnetic field and the radius, you can calculate the charge. If you know, basically if you know all the variables but one, you can calculate it. This was used to calculate the charge to mass ratio of an electron. They shot a stream of electrons, they measured the radius, they could measure how fast they were going, and they were able to get the charge to mass ratio of an electron. This is how they first got that ratio. They didn't know what Q was exactly. They didn't know what M was exactly. When I say charge to mass ratio, let's just go ahead and Q over M. They just divided the M over, they divided the V over, they divided the B over, so you get V squared over VBR. Bam. If you set an experiment where you know how fast electrons are going, and you know the magnetic field, and you measure the radius, you can get the charge to mass ratio, and that was the first experiment they did with it. Just basically a simple equation. Period, this is just to remind you all that, so like how long would it take it to do this? Period is the time it takes for one full revolution. That is just the distance it travels divided by how fast it's going, 2 pi r over v. Okay. We may not get to some problems today with this, but I'll quickly talk about a couple real-world applications of this. One is a mass spectrometer. So, what do? They shoot some particles through a magnetic field. They charge those particles in some way. They ionize them in some way. They ionize them all the same. If they have different masses, they're going to deflect different amounts. And so a mass spectrometer, you shoot a bunch of particles through it, you ionize them a little bit, give them a set amount of charge that you know, measure their radius, and you can determine the different masses of the particles. If you know Q, if you know V, if you know all those things, you can calculate the mass spectrometer. It's used to identify different chemicals that make up something. A very useful medical application of this is proton therapy, where they accelerate protons to a high speed using magnetic fields. So even CERN basically does the same thing. They use magnetic fields to make charges move, and they can get those charges moving faster and faster in a circular motion. And eventually, if you all have heard of proton therapy, it's super interesting. I want to talk about it. There's a field called medical physics, where there is certain medical procedures that you need to know a lot of physics. Proton therapy is one, MRI imaging, magnetic resonance imaging is another. Proton therapy involves accelerating protons to a high velocity. They use a magnetic field, and I believe they increase the magnetic field as time goes on, and they're able to accelerate them to a high speed, and then they shoot it into someone's body, and they use it to kill cancer cells. The really interesting thing about proton therapy is traditional radiation kind of kills. So let's say you have someone's arm, and it looks like a tube because I can't draw arms. When you expose radiation to it, say you want to do radiation therapy for someone who has cancer, that radiation is going to affect everything it hits. It's going to cause damage. I mean, the whole point of it is to kill cancer cells. And cancer cells are basically just normal cells that aren't doing what they're supposed to be doing. So radiation kills everything. So how do they pinpoint it? They hit it from a bunch of different directions, and where those lines intersect is going to be the main place where radiation delivers the most dose. That's how regular radiation works, but it kills everything in between. Like, if that's really deep, every part of your skin that radiation is hitting is going to be damaged in some way. Proton therapy is really interesting because what it does is they launch some protons into the skin, and the really interesting thing about these protons is if you do really fancy math, which I don't know, these protons release most of their energy when they come to a stop. So, yes, they're going through the arm, but they actually release most of their energy at the very end when they come to a complete stop. And so you accelerate these to a very specific velocity based on how far you're going and all that kind of stuff. And when they come to a stop, they release most of their energy. So if you have like a graph of their velocity over time, maybe their velocity kind of does this, but the energy that they release kind of does this. If this is the energy they release, this is their velocity as they enter this thing. And so they deliver most of the stuff at the targeted site. Super interesting application of some of these things, of accelerating charges and making charges go in circles. And I just remember going to, literally what I'm teaching you came from one talk I went to one time. I'm not an expert in this. UF, I believe, not UF. There is only a handful of medical centers that have the capability of doing this because they require such fancy equipment and giant rooms and all this stuff. So that's it. Next time we'll do some more problem solving. We'll talk about things going in a circle, force on a moving charge. Today, what did you learn? Moving charges experience a force given by QVB. Use the right-hand rule to find the direction of force given the other two. Those are the two things that we learned today. Moving charges experience a force due to a magnetic field. How do you find the direction of that force? Right-hand rule. And it causes them to go in a circle.
How you doing, Bosch? So this is what I was telling you about earlier.